This is the Circular Motion Lab, and there's 3 parts. 2 of them are conical pendulums, and 1 of them is a vertical pendulum. The purpose of the first part is to calculate the tangential velocity of an object and verify experimentally. This is a conical pendulum. You can see it has a shape like a cone, and if you exclude air resistance, the speed wouldn't change, but since direction changes, it has an acceleration towards the center.
So for this lab, we're going to use the equation v is equal to 2 pi r over t, where t is equal to the time and of one rotation, and r is equal to the radius of the base of the conical pendulum. When we were collecting data for this lab, we took a total time for the amount of rotations that we predetermined. We took 5 rotations, we timed it, and then divided that time by 5 in order to find our average time per rotation, and then use that to plug into the equation. To find r, we put a ruler down underneath the pendulum, and we're able to see from the rotations. We put the center point of the ruler at the center point of the base of the circle, and we're able to calculate the radius that way.
So this is the object. It is being acted upon by tension, which has a y component, which is equal to the force of gravity, and an x component, which is equal to mv squared over r. Tx is equal to the sine of this angle, and ty is equal to the cosine of the same angle. Since Tx is equal to mv squared over r and t sine the angle, we could say that the net force of in the x direction is t sine angle equals mv squared over r. Since ty is equal to the force of gravity and also to t cosine the angle, we could say that t cosine the angle is equal to mg, and if we solve for t, then mg over cosine angle equals t. You would then plug in mg over cosine the angle for t in this equation to get mg over cosine the angle times sine the angle is equal to mv squared over r. From this equation, you could say that the masses cancel out. You could also see that sine over cosine is tangent. So from there you'd bring r over to the other side and take the square root of both sides since v is squared, and you're left with the square root of r times g times the tangent of the angle is equal to v.
In collecting our data, we noticed that there were 3 spots where we could find error. The first of being the fact that as the conical pendulum is going in a circle, theoretically it should be a perfect circle, but in the real world it's not always a perfect circle, and most of the times it was making kind of an ellipsis shape. Second spot for error is when we were finding the radius with the ruler. We're just eyeballing it, so there could be up to, an 1/8 of an inch or centimeter off there. Furthermore, there could be timing errors just based on reaction time and based on judging where the pendulum started its rotation and where the pendulum ended its rotation. To conclude this portion of the lab, we took our value that we found experimentally using the equation velocity is equal to 2 pi r over t, and compared it to the velocity that we found from our derived equation, which is equal to the square root of rg tangent of the angle equals velocity. We compared these 2 values in order to calculate our percent error.
For the second part, the purpose was to calculate the tension of a conical pendulum and verify experimentally, so we're trying to calculate the tension in the string here.
For this portion of our lab, to find our theoretical value, we knew that Fg was equal to the vertical component of the tension. This allows us to use the cosine function in order to calculate the actual tension. Therefore, we can use this equation, tension is equal to mg over cosine theta, to calculate the tension. We found the mass, which is m in this equation, by using a scale in order to calculate the mass of the object attached to the pendulum. Gravity is a known value, 9.81 meters per second squared, and we used a protractor to measure the angle in this term, cosine angle. To find our actual value, since the force sensor only measures the vertical tension is equal to mg, and so we were able to calculate our actual value taking this information and the recorded value from the force sensor, taking the cosine of the angle, and calculating tension as we did in the theoretical portion.
A place for error in the second part of this experiment is that the force sensor rounds the value of mg to 3 places, which slightly can throw off your calculations. The purpose of the third part of the lab is to calculate the tension at the bottom of a pendulum swing and verify experimentally. In order to find the theoretical tension in a vertical pendulum, you could say that the tension in the x is equal to mv squared over r, and the tension in the y is equal to the acceleration due to gravity, which is mg. So you could set mg equal to mv squared over r, and to find v, you'd use the kinematic equation velocity final squared is equal to velocity initial squared plus 2 acceleration times distance, where the distance is the height between where the object is dropped and the bottom of the pendulum. To calculate the value experimentally, we swung the pendulum and then looked at the value that the force sensor gave us at the bottom of the pendulum. One place for error is that we had to guess where the bottom of the pendulum was when reading the tension from the force sensor.